Okay, let's do some more examples of computing Jacobians. So first of all, what is the Jacobian of the, well, it happens to be nonlinear. Not that, don't focus on that so much, but it's a nonlinear transformation. Okay, the key thing is it's a transformation. And here it is. So x equals u to the 2 plus v to the 3, and y is equal to u to the 4th times sine of v. Okay, so the Jacobian, let's see, so we should look at partial of x and y with respect to u and v. So we'll have here, let's see, take the x formula first, differentiate with respect to u, then differentiate with respect to v. So 2u and then 3v squared, and then take the y formula, differentiate with respect to u, and differentiate with respect to v. So with respect to u, partial derivative with respect to u, 4u to the 3rd sine of v, and then taking that same thing and differentiating with respect to v instead. So u to the 4th cosine of v, yeah? And then we need to take a determinant, yeah? So it'll be this 2u times u to the 4th cosine of v, then minus 3v squared times 4u cubed sine of v. Of course, you could do things like clean up u times u to the 4th as u to the 5th. We're not going to bother with that right now. And then just, though we're done with the question, just as a follow-up, it does mean that when it comes time, so in a substitution, future problem, in a substitution, dx dy gets replaced with the following. Well, it's let's stick it in parentheses, okay, just because there's two terms there. So in a set of, say, square brackets, gets replaced with 2u times u to the 4th cosine of v minus 3 v squared times 4u to the 3rd sine of v, close the parentheses, du dv. Let's do another one. How about if the transformation is x equals u times v squared and y equals sine of uv, what is dx dy replaced with? So the question format's a little different, but it is just another chance to practice the Jacobian. So just following what we've seen, right? Like here, dx dy gets replaced with Jacobian times du dv. So we'll just write dx dy equals, and then we're going to have the Jacobian here, times du dv, right? So we'll look at the x formula, u times v squared, differentiate with respect to u, and you get v squared here. Differentiate with respect to v, and you get 2uv. Then take the sine of u times v formula and differentiate with respect to u and with respect to v. So we've got a chain rule thing going on, right? So how about v cosine of uv and then u cosine of uv? And then if we just write this out a little more, which I think is still helpful, we'll have the diagonal entries v squared times u cosine of uv, then minus 2uv times v times cosine of uv, and then times a du dv, just copying that from right there. Okay, let's try another one. One more. So let's go ahead and same question format. Okay, so if the transformation is, let's say, x is equal to u cosine of v and y is equal to u times sine of v, then what is dx dy replaced with? So this time around, I'll just organize the work a little differently. I would just like to compute the Jacobian itself on its own first, just to organize the work a little differently. So partial derivative of x and y with respect to u and v, this Jacobian, it's going to be, so take a look at the u cosine v formula, differentiate first with respect to u, then differentiate with respect to v as the entries of the first row of the matrix. So with respect to u, we'll get cosine of v, and then differentiating with respect to v, let's see, cosine will differentiate to negative sine, right? So negative u sine of v. Then look at u sine of v and differentiate with respect to u first, and you'll get sine of v. And then differentiate the y formula with respect to v, and you'll get u cosine of v. Now let's just simplify this further. So this times that, right? So u times cosine squared v. And then when we do this times this, we need to subtract, except there's a minus sign right there. So why don't we just write a plus symbol? So we'll have plus u times sine squared of v. Let's factor out a u and have u times cosine squared v plus sine squared v. That's really u times 1 due to a famous trig identity, and we just end up with u. So in the end, okay, so this, the Jacobian simplifies to just being u. So this means that dx dy gets replaced with u times du dv. Now, what I'd like to do is actually follow up. I'd like to do the same question, to be really honest, but I'd like to replace the u's in this argument above. I'd like to replace all the u's that we see with r's, and also replace all v's that you see above with thetas, and something really neat's going to occur here. So I've got enough of, the start of that question is still here. So looking at the transformation is now x equals, well, instead of u cosine of v, u becomes r, v becomes theta. So we've got here x is equal to r cosine theta, and y over here was u sine v. Now we're saying y is r to replace the u, sine, and then theta to replace the v. What would you say about this transformation here? What does it remind you of? Hopefully this reminds you of polar coordinates. And then we'll skip all of the work here, okay? We could repeat it. It's just every u is now an r and every v is now a theta. But let's get the punchline right here. So what happens is then dx dy is equal to, well, u du dv, replacing the u's and the v's, becomes r dr d theta. Check that out. So what happened here is we're actually getting, this gives us a separate proof. Separate proof of the fact that dx dy, when you're converting an integral into polar coordinates, ought to be changed into r times dr d theta. So the question is sort of like, where did that r come from? We gave a geometric argument in the past, where still you might have felt some things felt a little left out. I get it. Here as well, there's a lot more theory that underlines some of this stuff, and we haven't gone through a bunch of theorems and proofs about some of the other things. But if all that other stuff behind the calculus really works, you're really seeing, just from a truly computational lens, why dx dy ought to get replaced with r dr d theta.